All right, so in the previous video, we talked about some basic terminologies, or how do we, what does it mean to be a differential equation? And basically, we looked at classification, namely order and the normal form. So let's take a look at a few other ways of classifying the differential equation. One of them is a linearity. So what is this linearity? So the linearity is basically whether the differential equation is linear or not. So we say a differential equation is linear if y prime, if y prime, y double prime, or any of the derivatives, right? Any of the derivatives are in the linear form. What do I mean by that? Either by itself, just by itself, right? It can be multiplied by functions of x, and that's okay, but you cannot have a nonlinear form in the function, the dependent variable, or the derivatives. What do I mean by that? You cannot have things like this. You cannot have y squared. You cannot have y prime squared. You cannot have square root of a second derivative. So these are all non-linear forms of the dependent variable or its derivatives. When I say dependent variable, you all know that when we say the function y is equal to f of x, x is the independent variable and y is your dependent variable, right? So this dependent variable y, right, this dependent variable y has to be, or the derivatives have to be in the linear form to say a differential equation is linear. So here is a very generalized form, as you see here. I have the nth derivative multiplied by, functions of x. I have a n minus 1th derivative multiplied by from function of x, another function of x. I have a first derivative, and I have a first derivative multiplied by a function of x, and so on, is equal to g of x. That's a that's a general form. Here's an example. So if you take a look at this one, y double prime y minus 2y plus y is equal to 0. Although I didn't mean it to be that way. Actually, I meant it as y double prime minus 2y prime plus y is equal to 0. That's perfectly a linear. The reason because the coefficient here is 1 and y double prime is by itself. The coefficient here is negative 2. The y prime is itself. It's a linear, and then y is also in linear. So therefore, this will be a linear differential equation. Let's take a look at some more examples. If you take a look at this one, y 2020, so there's a 2020 at minus 3x squared y double prime plus sine x y prime is equal to e to the x. So this is perfectly all right. Although remember, if you take a look, sine x, that's a nonlinear function, but that's in terms of x. It's okay. If you take a look at the 3x squared, that's a nonlinear function in terms of x, and that's okay. If you take a look at the e to the x, it's a nonlinear function, but it's in terms of your independent variable, that's okay, right? But as far as the dependent variables or the derivatives are concerned, right? This is the linear because the derivative is by itself, and here is a linear because that's a second derivative, and here is also a linear because it's a first derivative, right? So this is okay. So this will be a linear equation. There are more of them. So for example, let me show you a few other things in here. So if you take a look at this one, this would be a non-linear equation. The reason because you have y squared in here, right? And this also would be a non-linear. This also would be a non-linear because you have y cubed in here, and we have your y squared in here. And what about this one? What about this one? This one, it would be also a non-linear. I'll tell you in a moment why. Let's take a look at some other examples. Let's take a look at this one. This one would be a linear differential equations. The reason because the y prime is by itself, This is 2x times y, which is also in linear, and so that will be a linear differential equation. This will be a linear differential equation because the second derivative is linear, first derivative is in the linear form, and the function is also in the linear form. If you take a look at this one, this also would be a linear differential equation because the third derivative is in the linear form, second derivative is in the linear form, and this is also linear. So this will be a linear differential equation. And one other thing that I want to talk about in terms of linearity is the following, and that is sometimes if a dependent variable multiplied by a derivative of the dependent variable, if you have a term like this, then that becomes nonlinear. This is no longer linear. It's not linear. So if you have a term like this, anytime, it does not have to be y double prime. If you have y prime times a y triple prime, if you have a y times, the 20th derivative, anything that is multiplied, then this becomes non-linear, right? It becomes non-linear. So in general, by the way, if a differential equation is not linear, we call that as a non-linear differential equations. So as I've looked at some examples before, this is a non-linear differential equation. This would be a non-linear differential equation. This is a non-linear differential equation. This is a non-linear differential equation. What about this one? Right? What about that one? That's a non-linear. The reason because when you try to simplify this, you're going to have, y times a y prime minus x times a y prime is equal to y minus x plus 8. This is okay, and that is okay, but the problem is we have an issue over here. Now here y is multiplied with a y prime, and so therefore this is a nonlinear differential equations. And what is the homogeneous? We say a differential equation is homogeneous if it does not have, simply saying, if it does not have a standalone function of x. What do I mean by that? If you have a differential equation that is something like this, y prime minus 3y is equal to 0. If you take a look at this, I don't see any function of x by itself, right? This is a homogeneous differential equation. If it's not a homogeneous differential equation, we say that as a non-homogeneous differential equation. So what would be a non-homogeneous differential equation would look like? For the same function, for the same differential equation, if we have the following function, if we just say y prime minus 3y is equal to e to the x. Now you see, it does not have to be e to the x. I just wrote e to the x. It does not have to be e to the x. If you take a look, this e to the x is a standalone function, right, by itself, right? There is no dependent variable multiplied by it. Then that becomes a non-homogeneous. It does not have to be even this. It could be as simple as this. Y prime minus 3y is equal to 1. Now you have a standalone function that is, in this case, a function of x, in this case is a 1, right? You have it there. So it's a non-homogeneous. You can have a function like this. This is perfectly all right to have. For example, you can have y prime minus 3e to the x, y is equal to 0. Although you would see that, oh, I have a function of e to the x, but it is not by itself. It's multiplied by the y. Or you can have a function, you can have a differential equation something like this. E to the x, y prime minus 3y equal to 0. We don't have a standalone function of x. We have a function of x that is there, but that is being multiplied by the derivative of the dependent variable. But if you take a look at here, you have a standalone functions of x, and so therefore, this is a non-homogeneous differential equation. Another example of that would be, so for example, here is another example of a homogeneous differential equation as 3x squared minus sine x times 3x squared y double prime minus sine x y prime plus e to the xy is equal to 0. Again, I have functions of x in here. I have function of x, another function of x in here. I have another function of x in here, but they are not by itself. They are multiplied by the y or the y prime or y double prime. So that's okay. But a non-homogeneous version of this would be something like this, 3x squared y double prime minus sine x y prime plus e to the x y is equal to, let's just say, x. And that now you have a standard function. So this is a non-homogeneous. If I add another 1, that's still a non-homogeneous. I can add, cosine x. That's again a non-homogeneous. So that is the difference between homogeneous and non-homogeneous differential equations. And the most important thing of a differential equation, as a matter of fact, any equation, is finding a solution, right? Whenever we have an equation, whenever we formulate, whenever we model something into an equation, our goal is to ultimately to solve it, right? So the solutions are very important aspects, or finding the solutions, or methods to finding the solutions are important aspects of any equation. So what is the in general solution? So if I give you this particular equation, namely x squared minus 1 equal to 0, if I ask you to solve, you have some techniques, and you know how to solve them, right? You can use the techniques that you know, and then you would solve them. And then you would say, in this case, what you would do, you would factor them out. The technique in solving is either you can use the quadratic formula or you can factor them out. And you'd say, well, if I factor it, this is going to be x plus 1 times the x minus 1 equal to 0. So I have to set each of them to be 0. So if I set the first factor to 0, I'm going to have x is equal to negative 1. If I set the second factor to 0, I'm going to have 1. How do I know this is the solution, right? Well, if someone gives you this as an answer, what you would do normally is you would take a look at this and you would plug it into the original equation and see if it works. And then similarly, you would take a look at the other solution, you would plug it back in and see if it works. And that's how we verify whether something is a solution or not. So remember a couple of things in here. You have a differential equation, you know the technique, you know the process, you know the method to solve it. Once you solve it, you still verify whether this is a solution or not, right? And I don't have to tell you, you know this very well. If you have an equation, you may have possibly 3 cases. What are those 3 cases? You may have a solution to a differential equation, or you may not have a solution to any equation. For example, if I give you this particular one, x squared plus 1 equal to 0, this one does not have any real solution. This has an imaginary or complex root solution. But if I'm looking for a number, if I square it up and add 1 to it, that I want a 0, there are no real solution. So here's you have a case. I'm going to say no solution. Actually, as a matter of fact, I'm going to say no real solution, right? And you may have a unique solution. If you take for example, if you take a look at this x minus 1 the whole square equal to 0. Although it's a quadratic equation, you have only one solution. That one solution is x is equal to 1. You may have sometimes multiple solutions, just like the way that we have seen in here. X squared minus 1 equal to 0 has 2 solutions. X equals minus 1 and positive 1. So you have in generally, when you deal with the equations in generally, you have various cases, various ways of doing this, and this same is applicable for differential equations as well. So if you have a differential equation, you may have no solution to a differential equation. You may have a unique solution to a differential equation. You may have multiple solutions to a differential equation. For the same differential equation, you can have 5, 10, or sometimes infinitely many solutions. So now so what do we mean by a solution to a differential equation? What do we mean by a solution of a differential equation? So when we say a solution to a differential equation, we are looking for predominantly or primarily, we are looking for 2 things. So what is it? So we say a function phi. Defined on the interval. It has to be well defined on an interval I, right? And if it's a solution to an nth order differential equation, you should be able to find the derivative, possessing at least n derivatives, right? Not only that, the derivatives have to be continuous on your interval that you're looking for. And then, so basically, the function that you're looking for has to be differentiable as many as times the order of the differential equation. And then when you plug it back in, when you substitute this back in to that nth order differential equation, then it should satisfy that equation. So it should reduce to an identity. that equation should reduce to an identity. Basically, the left-hand side has to be equal to the right-hand side. If these two things happen, or if these things happen, then we say this 5, this guy, this function 5, we call that as a solution to the differential equation on that particular interval. So if I summarize it, so it should satisfy three things. Number one, it should be a function. I think this is we can go weaker on this. We'll talk about it, right? It does not have to be a function, but if it's a function, it's wonderful and awesome. But it does not have to be a function. We can kind of weaken this, but these two things are important. The y-f(x) should be differentiable, however way we can do, as many times as the order of the differential equation, and most importantly, even if it is not a function, even if it's a relationship, even if it's some sort of a curve or a closed curve, it doesn't matter, but it should satisfy the differential equation. What do I mean by that? When we plug in to the differential equation, the left-hand side should be equal to the right-hand side. So let's take a look at a very basic example. Is y(x) a solution to a differential equation y prime equal to 0? But before I go any further, let me ask you this. Is this a differential equation? It looks crazy, right? It looks very simple. Yes, it is a differential equation because it's an equation involving derivatives. So how do I verify whether this is a solution or not? Very simple. First of all, let's take a look if the function y(x) satisfies all three things we mentioned. So we are looking at the function y(x) is equal to 1. Property number 1, I'm going to say this is a P1, right? And this is a P2. And let's just say this is P3. Property number 1 is it a function? Yes, it is a function, right? Property number 2, is it differentiable? Can you find the derivative, right? Yes, as a matter of fact, I can find the derivative of y prime of y is equal to 1, whose y prime is 0. I can do the second derivative, that's also 0, third derivative. So it's not only one times differentiable, this is differentiable as many times as you can. So it's infinitely differentiable. You can find the derivative of the function y(x) is equal to 1 infinitely many times, right? Although remember, it's a first order. All I'm looking for is a function that I can find the derivative 1 times, right? You want it to be differentiable as many times as the order. Here the order is 1, so therefore I want this function to be differentiable at least 1 times, continuously differentiable at least 1 times. But as a matter of fact, what I got is like infinitely differentiable function. Now the third step, so therefore the second condition is also satisfied. The third step, or the third property is, does it satisfy the differential equation? What do I mean by that? This is the most important step. We're going to take the left-hand side, and then we're going to see if that equals to the right-hand side. So let's do that. In this case, the left-hand side is very simple. The left-hand side is y prime. In this case, y prime is equal to, since you're all experts, right, in finding the derivative. If you try to find the derivative of this one, you know that the derivative is equal to 0. So therefore, this is equal to 0, and which is the right-hand side. And so therefore, my function y is equal to 1 satisfies my differential equation y prime is equal to 0. Therefore, I can say yes, y(x) the answer is yes, because of all these three reasons. It satisfies the property number 1, it satisfies the property number 2, it satisfies the property number 3. Because of all these reasons, we know that this is a solution to that particular differential equation. I'll let you verify whether this is a solution or not. Is y equals x squared a solution to y prime? Right, go home and verify. Not only that one, I have some more questions here as well. Is y equals e to the x over 2 a solution? Y is equal to negative x over 2 a solution? And is y 2 times cosine x, ln of secant x plus tan x a solution to y prime plus y is equal to tan x? I'll let you verify all that. So the same way you can verify this. Let me solve this for you, and then you can do the other one. So how do I do that? Let me just maybe solve this for you to make your life easy. Again, the property number 1, in this case, whether this is a function, yes, it satisfies it's a function. And we are looking at a first order differential equation. All I want this function y is equal to x squared to be differentiable once. Yes, that y of x is equal to x squared. I can find the derivative once, and if I find the derivative once, that is 2x. That 2x is a continuous function, no problem there. I'm kind of skipping something in here. You will know in a moment. What do I mean by that? I'm not really talking about the interval. I'm not really talking about the interval, right? So keep that in mind. In this case, let's just say for the sake of simplicity, let's just say the interval that I'm working on is 0 to infinity. But we'll talk about it more in the next few minutes. So y prime is equal to 2x, so the 2x is no problem. If you take a look at the 2x, is continuous functions in the domain or the interval 0 to infinity. The third thing is the important, correct? So let's take a look at the RHS. We're going to set RHS. We're going to verify if RHS is equal to LHS. What do I mean by RHS? Right hand side. What do I mean by LHS? Left hand side. So if you take a look at the RHS, which in this case is y prime is equal to 2x, that we know. Let's take a look at the LHS. So this is your RHS, right hand side. Let's take a look at the left hand side. The left hand side is 2y to the 1 half, which is 2 times y is x squared and raised to the 1 half, right? And if I simplify this, that also happens to be 2x. So if you take a look, this 2x is same as this 2x. That means now I have the right hand side equals to left hand side, and hence this satisfies all three properties that we're looking for as a solution. And so therefore this will be a solution to that particular equation. All right. And I'll let you try this on your own and do this. As I talked about the interval of existence, right? So I kind of briefly mentioned the previous, a couple of minutes earlier. Let's take a deeper look at the interval of existence. So I have xy prime plus y is equal to 0, and x going from negative infinity to positive infinity. So is this a well-defined differential equation? So the question is, when I plug in x equals x into this, is this well-defined? No problem. As a matter of fact, yes, this is a well-defined differential equation. So, but the same differential equation, by the way, if I divide the differential equation by x in the throughout, then you would see that I have xy prime divided by x plus y over x is equal to 0 over x. And if I get cancelled, and if I simplify it, by the way, I get this, the same differential equation. But is this well-defined? And the answer is no. The reason because I have an x on the denominator and I have a 0 in my domain, and I cannot divide something by an x. So this is not well defined. Although it's equivalent, although it's an equivalent differential equation, right? But this doesn't work well for this particular form. This is not well defined on the entire real line. So can I do something else? Yes, this will be the only problem here. The only troublemaker here is x equal to 0. So if I remove the x equal to 0, I'll be okay. So if I ask you the same differential equation, is it well defined on this interval? The answer is yes, because this one does not have a 0. If I ask you the same differential equation, is it well defined on the positive real lines? Yes, it's okay. The reason because this one does not have a this interval also does not have a 0. So that's how we take a look at the interval of existence of a differential equation and then see whether a differential equation is well defined or not by looking at this. Now we can talk about a solution. Now we can talk about solution for the same differential equation, right? This is a well defined, this is a nice differential equation, right, in the entire real line. But the solution is go home and verify, see if it's a solution or not. And actually that would be a solution, by the way. Go home and verify, right? And verify that. That's a solution, but the solution is not well defined on this entire real line because again you have a 0 there. So the solution is well defined on the negative real numbers or positive real numbers, but not on the entire real line. Although the differential equation is well defined on the entire real line, the solution in this case is not well defined on the entire real line, but it's partially defined. It's well defined on the partial domain. In this case, it's a positive real line or not. So basically, what I'm saying is this function y is equal to 1 over x is a solution, not on the entire real line, but on either 0 to infinity or on negative infinity to 0, right? One of the two. But you can have both of them together at the same time, because then you will include 0. I mean, you can have both of them at the same time, but you cannot have the entire real line because you'll have a 0 where this is not well defined. Now let's take a look at this differential equation. Let's take a look at this differential equation. This is a wonderful differential equation, right? And what about this? And this is a circle. If you take a look at this, it's a unit circle. And if you remember your implicit derivatives, if you remember you were so long ago in your calculus with implicit derivatives, implicit derivative, you're going to have, this will be 2x plus 2y times the y prime is equal to 0. If I find the derivative of this equation with respect to x, if I differentiate this equation with respect to x, then I have this, right? And if I simplify this, right, I can cancel the 2. So I will have, y prime plus x is equal to 0. Then I can divide the whole thing by y. Then I would have y prime is equal to y prime plus x over y equal to 0, which is the differential equation. In other words, this circle right here happens to be the solution. But there's a problem in here. If I try to graph the circle, ladies and gentlemen, if I try to graph the circle, is a circle that I have here, is it a function? Is it a function? The answer is no, because it doesn't pass through the vertical line test. It doesn't pass through the vertical line test, right? So it's not a circle. Well, if you take a look at the half of the circle, yes, that's a solution, no problem. If you take a look at the bottom half of the circle, yes, that's a solution by and of itself. But all of them together is not a solution. And what do you call this? When I define the derivative, what do you call this? Remember I told you a word. We say this is called implicit derivatives. If you remember from your calculus 1 or calculus 2, we say this is implicit derivatives, right? And so therefore, we are going to use the same name to say these are not solutions per se, because for solutions, when we say solutions, we mean by a function, and the function has to be differentiable and so on. This is not even a function, so we cannot talk about the derivatives. Also, we can talk about the implicit derivatives, right? So we call it a solution. Also, they are not functions, but we can, by doing some splitting the functions in the top and the bottom, or you can do some a little bit of adjustments, a little bit of tweaking here and there, doing some tweakings. We can kind of make it look like a function, because I mean this circle, nice circle, satisfies my differential equation, right? So such a function, such a solution, right? Such a curve, we call that as an implicit solution. They're not really solutions, implicit solutions. And by the way, in future, from the rest of the semester, for the rest of the lectures, whenever we say a solution, we really not necessarily mean the solution in the strict sense, in the traditional, in the classical sense. We actually say a solution in the sense of an implicit solution. So whenever we refer to something as a solution, it's okay to refer to an implicit solution as a solution, right? So keep that in mind for the rest of the videos. Now, I'll stop it right here, and we'll talk about a few other things in our next video.